for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so hello everyone. Thank you for joining us today and welcome to today's webinars from our Standard Activity Board series. And today's presentations is from the IEEE Data Compression Standards Committee. My name is Edward Au. I'm the Vice Chair of the IEEE Computer Society Standard Activity Boards. Before we get started, I would like to address some housekeeping items with all of you. This webinar is being recorded. You can ask any questions in the Q&A box you can see from your screen. And also, the speakers will answer as many questions as possible. When submitting a question, please reference the slide. And the goal is to allow for a quick question or two after each presenter, and then we will bring all of our three presenters back online for a formal Q&A at the end of the presentation. A copy of the slides and the recorded webinars will be emailed to you tentatively tomorrow. Whilst today's webinar will highlight standards in word compression, the IEEE Computer Society actually has plenty of additional resources available for other emerging technologies. For example, our Computer Society Digital Library includes over 30,000 articles and peer-reviewed papers related to this topic alone. These include titles such as from one of our flagship publications, the IEEE Transactions on Knowledge and Data Engineering, which has a massive archive of peer-reviewed papers. Additionally, one of our flagship magazines, the IT Professional, features the latest technological highlights for developers and managers of enterprise information systems. You can get more information after the webinar because we will share it with you, but you can also learn it more at our official website, computer.org. Circling back to today's presentations, we are happy to have three honored speakers today. And as you may know, the topic is related to the efficient and concise data processing methods, which are essential to merge with successful business ventures. The IEEE Computer Society Data Compression Standard Committees focus on developing these cutting-edge data compression standards since 2019. Actually, I suppose some of you who are expert in this area may know more about, for example, the IEEE 1857 standards that are widely used today in different kinds of real-world and practical applications. Actually, as Dr. Neil will give us the history about her working group and standard committees, many initial members of this committee have extensive experience in developing the 1857. And in addition, we will hear from our second speaker, Professor Tian, about the IEEE 2941-2021 standard, which is a winner of the IEEE Standard Association Standard Emerging Technology Award last year. And later, after Professor Tian, we will also hear the update from Professor Zhang, who is our third speaker, also the chair of the 3184 working group, that they are trying to commit to use data compression techniques to resolve any real-world challenge related to highly efficient autonomous systems. All in all, I hope that we will have a live discussion with all the speakers about their work in data compression. And before we formally kickstart again, please note that as per the IEEE Standard Association by law, all the lectures, symposium, seminars, or educational course any individual presenting information on IEEE standards shall make it clear that this is their personal views and it is not the formal position, explanation, or interpretation of IEEE. And now I would like to invite Dr. Shan Liu to present her work about the Standard Committee. Dr. Liu is an internationally known technology leader and multimedia expert with brief and depth. She holds more than 500 granted US patents and has published more than 100 peer-reviewed papers and one book. She has won many awards, and she is also a fellow of the IEEE and also a distinguished industry leader of the APSIPA. She is currently a distinguished scientist and general manager at Tencent, where she leads teams of Tencent Media Lab, Tencent Video, and Tencent Games to build technologies and products serving over 1 million users. Dr. Liu, welcome again. Good morning, and thanks for coming and accepting our invitation to present your Standard Committee work. And please share with our audience your great work. Thank you. It's now your turn.
Thank you, Edward. Thank you very much. And good morning, good afternoon, good evening, everyone. And welcome to the seminar, the webinar, and presented by DCSC this time. My name is Shan Liu. I'm a vice chair of Data Compression Standard Committee, and it is my great pleasure to present on behalf of the committee today. Let me move over to the overview introduction about DCSC. So DCSC, as we can see from the name, it consists of two parts, DC and SC. DC stands for data compression, which is a process to modify a set of data and make its size smaller while maintaining all or partial important information. And why data compression is important? We all know that now we live in a modern world where data plays an important role. With continuous development and increasing demand for rich media and big data applications, and even though with the advance of storage and transmission technologies, the need for feeding more data into constrained storage space and data transmission bandwidth has never disappeared, and in fact has become more urgent. And take video as an example, as we use video every day. A typical high-definition movie file takes about 3 terabytes to store on the disk if it were not compressed. Well, we know that a standard single-layer Blu-ray disc can only take about 25 gigabytes, while a standard DVD can only hold about 4.7 gigabytes. So we see that there's a big gap between what the storage space in modern days can hold and how much a uncompressed file can take. So without compression, obviously video storage, downloading, and streaming can hardly be possible. And this also applies to other types of data. And not only data consumed by human, a big volume of data is nowadays also consumed by machines in broad applications such as video surveillance, smart cities, smart transportation, autonomous driving, and etc. So there are also market demands for new applications that involves volumetric data, which puts forward even higher requirements for data bandwidth and storage. And all these mentioned factors make data compression a technology field that has been around for decades as important and relevant even today. So then the second part of DCSC is SC, the Standard Committee, which is us. And our mission is to facilitate standard development of data compression technologies that reduce the volume of data while meeting requirements such as quality, clarity, low latency, security, confidentiality, and so on to the maximum possible extent. And in DCSC, our committee, our committee was established in September 2019 with the goal of exploring efficient technologies of compression, decompression, processing, and representation of data types such as video, audio, image, text, etc., and eventually to publish a series of international standards to facilitate those use cases. And we hold plenary meetings every about 3 months to keep our members informed of the status and progress. So DCSC began its journey with a group of researchers and technical experts who had long studied audio and video coding and compression technologies. And through the years, more and more joined us, and some of them carried extensive experience in standard development, such as from MPEG and AVS, including myself. And in 2012, this group decided to establish a standard working group under the IEEE SAB, that is IEEE 1857 working group. And after 7 years of work, several audio and video IEEE standards were published, and the interest of the group has expanded to broader areas related to data compression. And with the help of IEEE DCSC was formed, and some of the founding members of the 1857 working group became the core members of the new committee. Currently, we have 5 standard working groups covering areas of audio and video, AI model, digital retina system, autonomous driving, and Internet of Things. As mentioned earlier, the working group 1857 focuses on audio and video coding. The group has launched 12 projects, and 11 of them are already published, including 3 generations of audio, video, and system standards. And the working group 2941 mainly focuses on AI model representation, compression, distribution, and management. And the chair of the working group will give more information about this, the work in this working group just after this presentation. And they have won the 2022 IEEE SA Emerging Technology Award for developing the 2021 standard, and congratulations to the group. The working group 3122 was established in 2021 to explore technologies for intelligent data processing and compression for the Internet of Things. The ongoing project will define a framework for intelligent processing and compression of Internet of Things related data, consisting of compression and decompression, data representation and encapsulation, formats, encryption, and a set of tools. The data includes obviously video, audio, and also metadata such as time, location, objects, and sensors attributes, and possibly some AI-enabled analysis information. And also we have the working group 3161, which was established in 2022. The working group aims to define a series of standards of digital retina systems in which 3 streams with the video stream, feature stream, and model stream can work collaboratively for real-time analysis and processing of big data. And also about half year ago, we established a new working group, which is the data framework of for autonomous driving, the standard group, and the chair of the working group will give us more information shortly. And the goal of this group is to develop a set of common interfaces for autonomous driving systems to enhance the efficiency of information exchange among the various systems. So here is a list of all the standard projects under DCSC at the moment. And in summary, we have 14 published standards and 5 ongoing projects. And detailed information for each working group can be found in DCSC's website, and everyone is invited to check it out. And please feel free to contact us if you have any questions or comments. So next, I will give the floor to the chairs of Working Group 2941 and Working Group 3184 to introduce their work. And back to Edward.
Thank you so much, Dr. Liu. Thank you for your great overview of your standard committees. There are many parallel standard development work ongoing in your committee. Thanks again for developing the high-quality market relevant standards that are very important to our society, computer society, IEEE SA, and also IEEE. And we look forward to hear more from you and your members, and I hope your standard committee can have more awards in the future.
Thank you.
Thank you so much. So I do not see any question to you at this moment, so maybe we can go directly to Professor Tian. Thank you, Dr. Liu. So I would like to invite Professor Tian to deliver his presentation. Professor Tian is currently the Dean of School of Electronics and Computer Engineering, a distinguished professor with the School of Computer Science, Peking University in Beijing, China. And he is also a Deputy Director of Artificial Intelligence Research, Pangqing Laboratory in Shenzhen, China. He is a Fellow of the IEEE, a Senior Member of CIE and CCF, as well as a member of the ACF. As I mentioned at the beginning, his working group wins the IEEE SA Emerging Technology Award 2022. And Professor Tian is also a recipient of the 2022 IEEE SA Standard Medicant for his exceptional leadership for this 2941-2021 standard. Professor Tian, congratulations again for all the work and your leadership you have for the P2941. Please, you now have the floor to share with all of us the great work of this standard. It's your floor. Thank you so much. Please go ahead.
Thank you. Hello, everyone.
Yes, we can hear you clearly. Thanks.
Okay. My name is Yonghong Tian, and the chair of IEEE 2941 working group. Now let me introduce you to the 2941 working group. IEEE 2941 working group was officially established on September 24, 2020 under IEEE DCSC. Our standard scope is to define a set of tools for efficient AI model inference, storage, distribution, and management, including development, interface, interoperable representation, compact representation, coding format, and encapsulated format. Currently, we have 34 members from worldwide industries and academics with different aspects of the AI development chain. Together, we hold 11 plenary meetings and 17 workshops and receive over 80 contributions. We are developing 5 standards for AI models. One of our standards for AI models, representation and compression, has been published, and a standard for the AI operator interfaces will be published. Another standard about API of deep learning engine is in active part, and 2 standards are in preparation. And so IEEE standard, So IEEE standard 2941 2020, which is a standard for the artificial intelligence model representation, compression, distribution, and management under the DCSC 2941 work group, was officially published on March 18, 2022. As far as our knowledge, it is the first international standard to define the AI model representation interface and break down the barriers between computing architecture and algorithm frameworks. This standard compressed model compression ratio is more than 50 times under the premise that the performance loss of the AI model cannot exceed 5%. And the technologies of IEEE standard 2941, 2021 are based on neural networks, which are the replicated mechanisms of the human brain. AI-based as a deep neural networks, that is DNN for short, has achieved great success in a wide range of applications. And for example, the AlphaGo and ChatGPT give us a taste of the power of AI models. However, how do AI models adapt to different scenarios? And how do AI models interact with each other? We are facing diverse computing hardware, heterogeneous algorithm frameworks, and wide-scale AI applications. So there is no uniform representation of AI models, just as there are now many languages today. Therefore, standardized network and model representation are needed to bridge the gaps between different algorithm frameworks, and the compact model representation is also required for ease of deployment on different devices. On this basis, we can provide a standardized development and service interface for the application developer in different scenarios. So the standard consists of a 4-layer framework. The first layer is the interoperable representation format based on the neural networks, which includes networks, syntax, operation, definition, and weight format, as well as some data structures that can be used to define the compact or coded representations. The interoperable representation format makes it adaptive to a variety of computing architectures, deep learning frameworks, and application scenarios. And based on the interoperable representation, the second layer is to specify the compact representation of neural networks from different network compression algorithms, including multimodal pruning, quantization, and structured matrix. And this can enable the applicability of neural networks models on source constrained devices such as cameras, mobile phones, wearable devices, and so it can improve the runtime energy efficiency in both resource-constrained devices and cloud computing centers. So unlike compact representation, the coded representation is the coded representation format is to reduce the distribution and the storage costs for neural network models in the edge cloud computing and application paradigms such as city brain and mobile visual search. And after the AI model have been compressed, the encapsulated format will encapsulated with authentication and security information, which can provide intelligent property for AI models and support the authentication and security of AI models. During the project, the working group encountered many challenges and opportunities. The AI model contains a wide variety of AI frameworks, each operator unit is represented differently by more than, I think, 10 frameworks. Each member unit cooperates with each other to complete more than 200 operator definitions. Another challenge is the wide variety of compression algorithms and inconsistent evaluation criteria. After intense evaluation, we finally determined a unified evaluation system from the received contributions, which can well evaluate all compression algorithms. What's more, AI technology is developing rapidly. Standards need to keep pace with technological developments. Our team have been tracking industry demand and AI model development for 3 years. Based on this analysis, we finally developed this standard, which has certain foresight and can meet the industry need in a longer period of practical application. One of the key techniques is no-bit width quantization with multiple phase adaptations. Quantization is the most effective way to compress neural networks. This technique processes to reduce the performance loss by the quantization pipeline with clustering, shrinking, and retraining, and reduces the quantization bit width to 3 bits on ResNet 50, but the performance loss does not exceed 1.3%. And another key technology is partial weight sharing compression within layers between multiple models. The background of this technique is that we may have many AI tasks on the same devices, and theoretically, these tasks may need to use different models. For example, one model for face detection, one model for face recognition, and one model for image super resolution. So there is redundancy between models for different tasks. The answer is yes. This table shows the performance of super resolution multiple model compression in 4 different cases. The simplest case is to use one model, but with more performance degradation. Our method could achieve 1.56 model compression performance with almost no performance degradation. After the publication of the 2941 standard, we are very excited to see that many enterprises have adopted our technology standard. For example, the AI model interoperable representation has been implemented in several industry-level AI development frameworks. Some of the standardized model compression and encapsulation technologies have been integrated into the industrial chips and systems. Oh, why to slide? Oh, I'm sorry. There is some network problem. Oh. I'm sorry. Okay. Last but not least, I believe this standard has great market expectations and application prospect. According to the research, the AI market will reach $36 billion by 2025, and the AI models are becoming the core of AI applications with no doubt. 2941 is the first international standard that focuses on the barriers between computing architecture and algorithm frameworks, so it shows very good practicability and progressiveness. We believe that this standard can improve the AI model support for the intelligent economy and various social applications, and lead the development of basic hardware and software intelligent computing systems. And IEEE 2941.1 standard defines the functionality and specific input and output operators of AI operation. It considers both generality and efficiency and covers various types of operators, such as those related to basic mathematics, neural networks, and machine learning. It will help to reduce the complexity of AI software and hardware adaptations and improve the efficiency and portability of AI software development. And IEEE 2941.2 standard defines a set of application programming interfaces that can be used on different deep learning inference engines, including model management APIs, device management APIs, input, output APIs, and inference APIs, and so on. It will help to break down the barriers between different deep learning inference engines and applications. That's all. Thank you.
Okay, thank you, Professor Tian. Thank you very much for your presentation and the great work on the 2941, which defines the AI development interface that breaks down the barriers between the computing architectures and algorithm frameworks. This is a great work. And also, as notes from Professor Tian's presentation, the working group plans to develop a series of standards around AI model to meet the need of industry. And we will encourage you to join his working group and also Dr. Neil's standard committee for more work together. And Professor Tian, actually, we have a question from you from the audience. I hope that you can have a quick answer for that. They actually asked that because one of your slides mentioned about the ChatGPT. So the audience say that you also know, Professor Tian, ChatGPT is a very hot topic. So in the 2941, did you consider a similar GPT model as the 2941 application scenarios?
Yes, I think this is a good question. ChatGPT is a very big model. So this model can, in most cases, it can be used in the online APIs that with very backend with very powerful servers. So our standards can be used. What can be used to compress such a big model to maybe some smaller models can be deployed in edge devices. So traditionally, most of the compression algorithms in our standards can be used to compress such a big model to a smaller one. But such the ChatGPT is a very big model. So currently, our working group also developing some better technology to compress such a big model to a smaller one with less training costs. That is a very interesting work. If anyone can interested in this work, welcome to join us. Thank you.
Thank you. Thank you for your great response. Yeah. So as I also mentioned, so if there's anyone who is interested in the work, not only the existing published standard, but also the ongoing work Professor Tian mentioned about the 2941.1 and 2941.2, we encourage you to join his working group for more participation. And now, thank you again, Professor Tian. And at the end, we will go back to you for another Q&A. So actually, I would like to formally invite Professor Zhang as our first speaker. Professor Yang Yongjiang is a professor of the School of Computer Science and Technology at USTC Chengdu, China. She has 21 years of research experience in the areas of sensor networks, ubiquitous computing, and high-performance computing. And she has published more than 110 technical papers in these fields. She is an IEEE Fellow, and also she is the winner of the ACM MobileCom 2021 Best Paper Winner-Up Award. Professor Zhang, thank you very much. Please share with our audience the work your working group is doing. And now it's your turn. Thank you again.
Sure, thank you. Thank you, Edward, for your nice introduction. So today, it's a great pleasure to have this opportunity to talk to you about our working group 3184. Compared to what Dr. Tian just presented, our working group is like an infant. It's still in the baby stage. So you basically heard something that's really mature and well developed, and now you are hearing something that's really still in the starting phase. And also, Professor Tian's working group is more like algorithm focused, and our working group is more systems focused. So it basically really presents a different trend in this whole thing. So our working group is called Data Framework for Autonomous Driving. I am Yan Yang, and I am the chair of this working group. And I'm working with my colleague, Professor Yu Zhang, and she is the vice chair, and our secretary is Professor Li Li. We are all from University of Science and Technology of China. So as I just mentioned, we are very new. So we got reviewed and approved like in less a year ago, April 29th. So we got approved for a new working group. Then, actually, even our PAR was received the approval in June last year. So this is really a short time frame. We had the opportunity to have like 3 plenary meetings. We discussed about the scope of the working group. And in the last meeting, it's fortunate that we got our first 2 proposals. And I'm going to talking about them in this talk. All right, so what are we? What are we about? Basically, it's data-related architecture for highly efficient autonomous driving systems. And basically, the scope includes the architecture components, interfaces, transmission protocols, and connection protocols. All of these different aspects of the data framework, data architecture are included. And we also provide the definition of efficiency. What do we mean by efficient autonomous driving systems, including metrics for accuracy of perception and decision-making, the latency of the required computation, as well as the energy consumption and the power consumption of the sensors and computation in this whole system. So basically, it's if you think about it, it's everything about the data that's involved in a self-driving system. So why are we here in the data compression word? That's basically data is driving the development of autonomous driving systems today. And this is, since we are really just starting, we don't have too much of Professor Tian just said they had like 80 contributions, and we only got 2 here. So this is our tentative plan of our working group. Basically, 3184 is the overview and of the autonomous systems that include the subsystem and their relationships. Then we have point 1, in which we talk about sensors. And then we have 3184.1.1, and we talk about the roadside infrastructure and the data that's coming out of there. And then point 1.2 is the vehicle-related sensors and their data. Then 3184.2, we want to focus on perception methods and the data coming in and coming out of the methods. And the 3184.3, we plan to focus on planning and the decision-making methods. And point 4, we want to talk about computing systems and all the computer system-related techniques for autonomous driving. And then point 5, we want to focus on cloud control systems and the connected cars, all that big picture. Then point 6, we want to focus on communication protocols for CCS. And point 7, we want to focus on data compression in this whole system. And point 8, when your cars collect a lot of data and also send the data to neighboring cars and the roads and the clouds, privacy will become a serious concern, and we want to focus on privacy protection in 31.84.8. So now we have like 2 new contributions, and I will go through them just in a little bit. Well, first of all, I want to give you guys a little bit of background of this whole thing. So in today's world, we have cloud-connected cars, we have smart roads, etc. So if you look at this picture, that's the future that actually not the future, it's the current future that we are heading towards. You have connected cars, you have sensors on the roads, connected roads, and all of these entities that collect data through their sensors, and then they pre-process the data on these cars and on the roadside units, and then they transmit the data to the clouds. If you look at the clouds, the clouds can be categorized into edge clouds that are the closest to cars and the roads. Above them, we have regional clouds, and then we have center clouds that really make like large-scale decisions. So within this system, we need to look at the communication perspective, such as vehicle-to-road communication, vehicle-to-vehicle communication, vehicle-to-cloud communication, road-to-clouds, and the clouds-to-clouds. A lot of styles of communications are happening, and a lot of data are being exchanged. Then, of course, with the data, we want to run perception models on the vehicle side, on the road side, and also on the clouds. Based upon the perception results, then we can we go through the decision making both on the vehicle and in the clouds. So that's the big picture of the entire system. Then I was also asked to present a few example key technologies that are related to data framework for autonomous driving that will greatly benefit this working group. So related to autonomous driving, as you can imagine, there are tons of technologies. And here, due to the space limit and the opportunity else. First, technology EV, bird eye view based perception and navigation. Then there's the sensor calibration and also offline reinforcement and learning based navigation. We also have the model performance evaluation and the data compression. So these 5 key technologies, they are all data-driven approaches, and altogether they can be used to form a closed loop platform for autonomous vehicles, which will enable data to substantially benefit self-driving. So next, I'm going to go through these 5 technologies one by one. First one I want to mention is bird eye view, BV-based perception and navigation. So today, actually, I think from last 2 years, it has become really popular that to conduct perception on the BEV perspective using the BEV features of the word model. So we could have multimodal BEV perception that takes the multimodal sensor data and by running the multitask deep neural networks, and we will get the BEV perception results. And based upon the BEV perception results, we can have reinforcement learning-based BEV navigation. And from there, it's easy to conduct a safety verification and the path planning. So that becomes a L4 mapless autonomous driving system. So what is the potential impact of this technology? Basically, up to now, if you look at it, most practical autonomous driving systems, we are not talking about research systems, but practical and working in the real world kind of systems, they all rely on high definition maps. I wouldn't say they all, but most of them rely on high definition maps. And this BEV-based perception and navigation technology can very likely lead to mapless L4 autonomous driving systems, in which we can build a 3D map of the surrounding area in the runtime as the car runs, and identify static and dynamic objects in the environment as we go, and estimate the motion state of the vehicle itself. So it basically removes the high definition maps. Well, if you have the HD maps, it's still good, but it does not necessarily live by the HD maps. So that's the benefit of this technology. It's totally data-driven, as you can see. We rely on the real-time data that comes into the sensors and goes through the perception models. The second technology I want to mention is called sensor calibration. In the big system that I just showed, there are smart cars, there are roads, smart roads, and then there are different layers of clouds. So if you want to piece all this data, all this information together to form a big picture, then how to perform accurate sensor calibration, both temporal and spatial, will become extremely important. So here I want to mention 2 points, 2 issues that we are looking at this moment. One is how to calibrate 2 neighboring LiDARs. Well, you can imagine on a intersection, we deploy 2 LiDARs that cover the roads to monitor the traffic. And in order to basically fuse the data that's coming out of both LiDARs, we need to calibrate them and synchronize them. And why is this a hard problem? Because the LiDAR data is low resolution, and the features could be really sparse if you look at the environments, and there are lots of noises. So in this case, we propose to use spatial features, even sparse in the environment, to achieve spatial calibration, to achieve the initial spatial calibration. And since these features are sparse, the initial calibration isn't that accurate. Then on top of that, we use the trajectory of moving traffic objects to achieve more accurate time and space synchronization. And the good thing about this method is as more cars drive by and as more people walk by the LiDARs, the more accurate the system will become. So this is the first synchronization technology I want to mention here. The second is, imagine on the highway, you actually want to also monitor the traffic, you want to monitor the accidents, you want to see whether there's a congestion, so you need to use sensors to do that. In this case, imagine that you have a camera and a millimeter wave radar on the same pole, and they work together to provide the monitoring function. And in this case, you have to calibrate these two different sensors to make sure they can work together. And why is this problem hard? Because there's a huge density gap between a camera and a radar. And the radar data is extremely sparse. And the ultra low resolution for radars. And radars produce ghost points, etc. So it's a hard problem. And in this case, we propose to first you estimate the vehicle occlusion situations using the image data, because image data does not see through vehicles while the radar data does. And at the same time, we can embed depth using transformers to maximize the benefits of radar. So to basically calibrate them and these methods actually yield very good results. The spatial calibration error is reduced to the centimeter level, and the time dimension reaches interframe synchronization, and time error is less than 1.5 milliseconds. It's really amazing. And the camera and the radar fusion method can significantly improve the perception accuracy on the highway, and you can see as far as 500 meters, and that's basically quite amazing as well. Then the third technology I would like to mention is offline reinforcement learning-based navigation. So deep reinforcement learning based navigation for mobile robots is a hot topic right now, and we are also conducting research in this area. So first, you train a navigation policy for mobile robots using DRL, and then the navigation takes the BV features that I talked about earlier as input and goes through the model and outputs the possible trajectory. So this is how this the RL-based navigation system works. Well, why do we want to make a standard out of this navigation method? Because it can make it applicable to more settings, mobile robots and small cars, like robotic-like cars and the minibuses, and in city roads, on the campus, and even in some mountains. And by making a standard, so it can be applied to many, many different settings. It's also easier to generate the data needed, and it's also easier to understand the output trajectory, because the trajectory format will also be standardized and to make it into a uniform format. And then that's the three perception and the navigation related technologies. And next, the fourth one is actually computation related technology called model performance evaluation. So what do we mean? If you think about an autonomous system, if you think about a smart road and a cloud controlled system, there are so many different deep learning models that are being used in the system. All the perception algorithms, most of them are deep learning models, such as the camera-based, the LiDAR-based, the radar-based, and how to fuse them, how to navigate, how to perform the SLAM. All of them could use deep learning models. And then these models are getting larger and larger, and some efficient model variants keep coming up because the community realizes if you make the model bigger and bigger, they just don't fit on your car or your robot. But these variants are often computationally friendly, but not latency and energy friendly, and we are also not sure about their accuracy. So in this case, we really need to evaluate these models. Here, we propose a model substructure operator. It's a hierarchical performance evaluation framework. And this framework can take into account the influence of the hardware architecture that you want to deploy these models on and the model structure itself. So it will become really useful. And what is its potential impact? By standardizing of the hierarchical performance evaluation framework I just mentioned, we could make it easier to find performance bottlenecks and then optimize them easily. And we could make it possible for real-time perception on the roadside and on the vehicles, and even on the robots, and even on your smartphones. So this, we really look forward to this evaluation framework standards. So this is the first technology. Well, just bear with me. This is not really responding. Oops. Oh, I think it's my network problem. So let me come back. Let me turn off my camera so that I can save some. All right. So the last technology I want to talk about is data compression. Professor Tian talked about video compression, and here we talk about the point clouds, the LiDAR point clouds compression. This is really important for our system because LiDARs are one of the primary sensors in autonomous driving. And the current LiDAR point cloud compression schemes are mostly based upon octrees and cannot fully utilize the physical prior of the LiDAR point cloud capture system. And to address this, we propose to compress range images instead of the original point clouds in an end-to-end manner. And by making this into a standard, we could make it possible for point cloud-based machine vision, can make it possible for efficient V2X communications, because especially for those vehicles that use LiDARs, and also can make it possible for efficient storage compression for machine vision. So it basically provides a tons of benefits. All right, so now we got, this is really exciting. A lot of people, I think we have almost 30 members enrolled, and we got 2 contributions. The first contribution is the road cloud data exchanging platform. If you look at this, we basically defined a data exchange architecture between roadside infrastructure and the cloud control platform. And based upon this framework, we can define the interface of the data transmission module between the roadside and the cloud platform. And also the input and output interfaces of the roadside multi-sensor fusion models, and the interface definition for uploading results, the perception results to the cloud platforms also defined. So we are very excited about this contribution. The timeline is we hope to approve this part actually in a meeting that's coming up, and we hope to have a working group draft next year. And the second contribution is a road network description contribution. So if you think about autonomous driving, if we want to test whether the navigation policy is working okay, and if the driving plan is safe, we actually need to run through the navigation plan in very specific things and in a lot of different challenging things, but we do not have the resources to collect real data for these things. So what we do is we can use simulators to generate the things. And here, this standard, this contribution is about how do we describe the road networks in such, when you want to generate things in such simulators. We want to standardize this definition. So here, it's based upon road network entities. These are fundamental building blocks of the road network data structure, and also the relationships between them. These relationships are going to define the topology of the road network. And this contribution also, we hope to approve it as a part in the meeting coming up. And it will become a working group draft in next year, March. And that's basically the situation with us. And looking into the future, we really, our working group aims to provide a unified data-related architecture for highly efficient autonomous driving systems and connected cars, and also the cloud control platforms. And here, we sincerely invite autonomous driving related companies and institutions, researchers, to join us to develop the data framework and promote the development of our community. And it goes without saying that this industry, this domain is very important, and it will be part of our future. It's here to stay. All right. So that's my introduction of our working group.
Okay, thank you so much, Professor Jiang, for your extensive summary of the working group you are chairing and the work your working group covers. You know, today the data frameworks of all these subsystems is designed individually, which usually limits the efficiency of the information exchange among different subsystems. And the need of common interface slow down the fast development of autonomous driving related perception and planning algorithms. I personally believe your working group is doing a great job to resolve this kind of real-world challenge to have a standardized common interface for these subsystems. And actually, I know that we are already overrun, but we have two questions for you, Professor Jiang. And then actually the first question is that many aspects of the autonomous driving system work standardization, and the audience asks why do you select and why you and your working group prefer to standardize the data framework but not the other component? Why you focus on data related framework?
Oh, it's a very good question. So basically, I think autonomous driving system, well, it's all about data. So it collects data, it processes data, and based upon the processing results, you navigate. So it is all about data. That's why we make it data-centric. I think the data framework, in a way, actually covers every single aspect in this whole thing, if you really think about it. So if you have some contribution that's related to autonomous driving, smart cars, smart roads, even if you don't have the data in your title, I think it probably fits, and contact us and join us.
Okay, great. And then another question is, our audience asks if there is any related or similar standard in ISO, I mean in the ISO, IEEC, that is related to your work. If no, do you and your working group and standard committee have any plan to ask the ISO to endorse your IEEE standard?
I think the ISO, there are a few that are marginally related, and we definitely, after we develop a little bit further, and we have our parts and also contributions more solid, we definitely plan to work with them and to see how to connect and to push this community further together.
Okay,
and thank
great.
you for your suggestion.
But thank you so much. Thank you for all the information and the way that people can join your working group for standard development. Thanks again, Professor Zhang. And then
Thank you.
lastly, Professor Tian, actually, I know it's time running out and I apologize, but there are two short questions. Are you willing to answer some of them, Professor Tian?
Yes.
Okay, great. One quick question is because the audience say that your P2941 is doing some great work, not only the published standards, but also the Doc 1 and Doc 2 that are ongoing. In addition to the standards, does your working group also plan to develop any reference software that can be available for implementers? Do you have any plan from your working group?
Yeah, I think this is a good question. Actually, we have developed such your reference software, and currently, and actually, the reference software may be written in different developer frameworks such as the PyTorch and the TensorFlow, and I think another one is maybe from Baidu's PaddlePaddle. And so we actually have some plan to open this reference software to the public after making some, I think, coding improvement. We also open to the working group inside, and finally we also wish to open to the public. I think from the GitHub. It's okay.
Okay, great.
Maybe sure.
Thank you so much. And another one, I thought it is more about a comment because the audience say that your working group 2941 are very meaningful, especially the 2021 standard. And actually the commenter asked for any future standard promotion plans. I believe it's already covered by your slide that I show here that you all have ongoing 2941.1 and 2941.2. It is the case, Professor Tian.
Yeah, I think this is a good question. Actually, we, beside the point 1 and point 2, we also have some other parts in preparation, such as for big model. I remember in the last questions, I also mentioned that we are developing some two standards respectively for big model compression and graph neural network. These are two standards we are going to, and we plan to submit the PAR in maybe I think June or September. I think maybe at that time. Because we before our submit the part to IEEE NITCON, we need to do some technical analysis and some preparation for the standard study. So if anyone also interested in the two standards, also welcome to join us.
Okay, great. And thanks again, Professor Tian, for your quick response to these two questions. Okay, now we actually go to the end of the presentation. Again, I would like to thank Professor Tian, Professor Zhang, and Dr. Liu for joining us today and share what is going on in the world of data compression. A quick programming notes. The next webinar of the IEEE Computer Society will be entitled Present Persons with Impact from our Build Your Career webinar series. That webinar will be scheduled on March 16 at 11 a.m. Eastern Time. And lastly, once again, I would like to thank all of our speakers today and our society staff for joining us today and for all of you attending and for lively Q&A discussion. Thank you again and have a great rest of the day. Thank you. And now the webinar is concluded. Thanks again. Take care.
Thank you. Bye.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Scott.